Well, this is an exam review for exam 2. And basically, we are here talking about forces acting because this exam has chapters like Newton's laws and applications of Newton's laws. So when you look at these questions, try to understand them. Try to understand what the forces are, the directions in which they act, and then it'll be quite useful for you on the exam. So in the first one, we have an object tied to a string right here, an object tied to a string, and that is the other end is tied to a pole, and it's going around in a circular path like that. So it's making a circular path. As soon as you hear about a circular path, the force that should come to your mind is the centripetal force. Any object moving in a circular path will have a centripetal force acting on it. So this is 100 centimeters long, the string is, and the angle is 20 degrees. The mass of the object is 20 grams. When you look at the forces acting on the object, always remember the weight of an object acts vertically down. That should be the first force that you draw, the weight of an object. And the weight of an object is its mass multiplied by the acceleration due to gravity. So mass must be in kilograms. Here it's in grams, so in kilograms it will be 20 grams divided by 1,000, which is 0.020 kilogram, times 9.81. So the weight of an object always acts vertically down. The other force is the tension in the string, and that acts straight up. And then you see that the tension being at an angle can be broken up into its vertical component and the horizontal component. The vertical component is going to be t cosine theta. So that's t, and you find the angle here is theta. So this is going to be t cosine theta, because this is the adjacent side of that little triangle there. So the vertical component is t cosine theta, and the horizontal is t sine theta. Now we don't need the horizontal component in this case, because you can immediately see that t cosine 20 is exactly equal and opposite to the weight. So t cosine 20 should balance the weight. That's all we need. So t cosine 20 is equal to mg. And the mass is 0.020 in kilograms times 9.81. That means t is going to be that product divided by cosine of 20. I've done all that and I get 0.20 newtons. So all we needed was to break up the tension into its vertical component and set it equal to mg. Why and how could we do that? Because we know that it's moving around in a horizontal circle. So there is no movement vertically. That's why we knew that the net force along the vertical or along the y-axis must be 0. That's why we set them equal to each other. Very important point. Let's move on to the second one. So motion of an object on an inclined plane is really important. So you have an incline and you have an object kept on the incline. Like I said before, the first force that you're going to draw is the weight. And weight always acts vertically down. But one big difference in this case is that the x-axis is going to be along the plane and the y-axis is going to be perpendicular to that. So keep that in mind. We'll get there. So this is the object, and that's the weight acting. Weight acts vertically down, and this is the normal force. So the normal force is in place of tension. So remember, when you have a string, the force is going to be tension. But if you have a solid surface, then it's going to be the normal force perpendicular to it. Don't draw it any way you like. Not like that, not like that. It has to be perpendicular to the surface. So if that's the surface, It's got to be perpendicular. So those are the two forces here. And then because we have set up the x and the y axis, we will see, okay, here I'm also assuming that there is friction. If there is friction, it could either be down or up, depending on what direction you're trying to move the object. So, assuming that we are trying to push the object up, so there is a force applied upwards, which somebody applies. That's what is shown here. And then friction should be opposite. So friction is down the plane. So those are the four forces. Again, the weight, always vertically down, the normal force, perpendicular to the surface, the applied force that somebody is trying to apply to move it up, and then friction, which is opposite to the applied force. So you see that these two forces, 1 and 2, are along the x-axis. See, one is along the positive x, the other is along the negative x. This is along the y-axis. But the weight is neither along the x or the y. That's why we're going to break the weight into its components. Let's do that. So the weight is mg. The applied force is caps F, the frictional force is little f, and the normal force is n. So here I have the x and the y-axis. Clearly, these three forces are either along the x or the y. This one is the culprit, so you got to break that into two. Okay, we're going to do that there. I've drawn the green arrows a little off so you can see them. So this is mg cosine theta, because this is going to be theta, which will be the same angle as here. So if this is theta, whatever, 20 degrees maybe, this is also going to be 20 degrees. So this is mg cosine, and this is mg sine. Okay, so let me draw that right, and then I'll draw it again down below to show you. So here are the three forces along the x-axis. The three forces along the x-axis are mg sine theta, friction, and the applied force. See that? You apply the force upwards, you have friction down, and you have the component of mg, which is mg sine theta opposite. Okay, fair. So when you try to find the net force, you already see that you're trying to push the object, so that should be positive, and these two are negative. So when you write down the net force, remember that. Okay, and on the y-axis, there are only two forces. One is n, the other is mg cosine theta. And since the object is not going anywhere along the y-axis, we know they should be equal to each other. They're equal and opposite, okay? So another thing that comes in is, remember that friction is always mu times n. Friction is mu times n. Mu is the coefficient of friction. Yes, and n is the normal force. So friction is mu times n, but remember that in this case, n is mg cosine theta. So friction is mu mg cosine theta, and then we take the net force along the x-axis. So the net force along the x-axis is F, caps F, minus mg sine theta. Why? Because F is positive and the other two are negative. These two are negative. And then we substitute for friction. That's all. Friction. Friction is mu mg cosine theta minus mg sine theta. So that's the net force along the x-axis. So if you can remember this stuff, if you can really understand this stuff, you're going to get more than 3 questions on the, or let me say about 3 questions on the exam. You really have to understand this. And I'm going to work another problem out using the same ideas. So you see it again. So you see the applied force, the weight, the normal force, the weight broken up into 2, the mg cosine, mg sine. Now, you see, I'm doing it a second time so you can see it. Those are the forces. That's the x-axis, that is the y-axis. The net force along the x-axis, which we have written before, And according to Newton's law, the net force should be equal to mass times acceleration, right? Mass times acceleration. So the left-hand side, we have already seen, is F minus mg sine theta minus friction is equal to max. And friction is what? Mu mg cosine theta. Okay? Mu mg mu n. And so I've split it into so many steps again. Same thing as before. Now I'm going to substitute for n as mg cosine theta. It's max, and then I can find ax. And I'm just giving some values. Assume that the applied force is 100 Newton. Trying to work out a problem, so to say. Mass is 2 kilogram. Theta is 20 degrees, and mu is given. Then plug all those numbers into this, okay? So you have 100 minus 2 mg sine 20 minus 0.200. Man, I thought I should write it on this side because I don't have space there. So let me just scratch that out and write it here. Okay, so again, 100 minus 2 times 9.81. It doesn't matter if you use 9.8 on the test. It doesn't matter. Just use 9.8. Minus 0.2002, 9.8 cosine of 20 is equal to 2 times ax. And so the only unknown quantity is a sub x, which is the acceleration along the x-axis or the acceleration along the plane. So you get those numbers. That number is 100, of course, and this is 6.71, all of this. This is 3.68. You just do the math there, and you get quite a large acceleration because I'm applying a huge force, okay, 44.8 meter per second squared. So there it is. Very important question. Motion of an object on an inclined plane. All right, so remember that. And then here is another one. So here, simply you have a string with an object at one end and you're just holding it there. And if I ask you what's the tension in the string, that's quite easy. There are only two forces. mg is down, tension T is up, so the tension in the string is just mg, right? T is mg, that's it. Okay? So if you're just holding it there, that means the acceleration is 0. You're not moving it up. You're not moving it down. The acceleration is 0. Then the tension is equal to mg. On the other hand, what if you were just not holding it there? What if you were accelerating it up, yanking it up with an acceleration? Now the tension in the string increases. Okay, so let's look at that. So you have the same weight, you have the tension, but now you're moving it up. So the acceleration is something like 2 meters per second squared and up. In this case, you have to remember, because you're moving against gravity, the tension is going to increase. So tension would now be m times g plus a. G plus a. Just remember, it's going to increase. But what if you were moving it down? Instead of yanking it up, like you were bringing it down with a certain acceleration. In this case, you're moving with gravity, so the tension in the string decreases. That means now the tension would be mg minus a. See that? Yeah. mg minus a. All right. So if you take m as 1 kilogram and then you try to work all this out, just assume that the acceleration is 2 and you're trying to move it up at 2, then moving it up, it will be 11.81. You can see the math there. But if you were moving it down, then it would be 1 times 9.81 minus 2. That would be 7.81 Newton. And if you were just holding it there, it would be just 9.81 because it's 1 times 9.81, just 9.81. That's something else. And then we have a situation where you have an object that is actually moving with a velocity. It's like a book that you throw on a carpeted floor. That book is going to stop. Okay, why did it stop? Because of friction. So friction did some work in order to stop the book. So now you got to think about, did the book have energy? Yes, it had kinetic energy. So whatever kinetic energy it had, friction had to do that much work in order to stop it. You know what I'm saying? So whatever kinetic energy the book had, friction has to do exactly the same amount of work to stop it. Okay. So if the velocity is v and the mass is m, and if it stops in a particular distance d, then we know we can calculate the coefficient of friction. How are we going to do that? Kinetic energy is 1/2 mass times velocity squared. Don't we know that? Yes, we do. And the work done by friction is force of friction times distance. So in this case, let's assume that the mass is 2 kilogram and the velocity is like 5 meter per second. The velocity is 5 meter per second, right? So first, remember the kinetic energy is exactly equal to the work. So that's why I put kinetic energy is equal to the work done by friction. Calculate the kinetic energy. 1/2 times 2 times 5 squared is equal to, we do not know the force of friction, so F times, the D is 10. So now we get the force of friction, don't we? On the left side is 25. On the right side, you have F times 10. That means F is 25 by 10, which is 2.5 newtons. So the force of friction is 2.5 newtons. And then you look at the free body diagram. Because it's a horizontal surface, remember, the weight acting vertically down should be equal to the normal force. So now there is no cosine and sine. It's fairly simple, mg and n. OMG, okay. So n and mg there, so n is equal to mg. And we're trying to find mu. We know the formula for mu is F by n. But in this case, because n is equal to mg, we can substitute mg for n and then plug in the values of mass. Okay? Mass is 2 kilogram. So 2.5 by 2 times 9.8. And that would give you the answer. So that gives you 0.13. Gives you 0.13 as the value of mu. So the next one is based on the work energy theorem, where you know work done is equal to change in kinetic energy. Work done is equal to change in kinetic energy. So if you have an object that is moving, all right, and you make it move faster, you're doing some work, because you'll have to apply a force and then make it move faster. So if you want to find the work done, all you got to do is find the final kinetic energy minus the initial kinetic energy. That's all. That's called the work energy theorem. So you see the work is equal to final kinetic energy minus initial kinetic energy. Here's an example. So just take the initial velocity as 5 meter per second. And the final velocity is, well, that is a little slow. So 10 meter per second. Now it's too fast. And the mass is 2 kilograms. So now you can find the work done just by using this formula. Half times 2 times 10 squared, because that's the final velocity, minus half times 2 times 5 squared. Okay, so that means now this one becomes 100. And on the other side, you have 25. So the work done is 75 joules. That's it. So work done is equal to change in kinetic energy. All right. This one, I'm just going to give it to you. You know, this is the work done in extending a spring or compressing a spring is 1/2 kx squared. K is the spring constant, isn't it? K is the spring constant, and X in meters must be the extension or compression. K is 10 Newton per meter and X is 5 centimeters. Then, the 5 centimeters is 5 divided by 100 in meters, so it's 0.05 meter. And the work done would be half times 10 times 0.05 squared. So that comes out to be 0.0125 joules. By the by, the work done in a spring becomes its potential energy. So if you're asked to calculate the potential energy of a spring, you will again use the same formula, 1/2 kx squared. It's the same thing. So whether you're asked to find the work done on a spring or the potential energy of the spring, you use the same formula. Right, so this one we talked about, so we don't need that. And here is the last one. So here you have two objects. One of them is on an inclined plane. The other one is hanging down, with a string passing over a pulley. So you have to, let's say this is M1 and this is M2. And you have to find the acceleration of the system. So if you let go, mass M1 is going to come down and M2 is going to go up the slope. And we have to find out with what acceleration both move. Obviously, both have the same acceleration. So in this case, we have to carefully look at the forces acting on each one. What are the forces on M1? Two forces. You got it right. One is the weight acting down, the other is the tension. Which one of these two forces is bigger? Think about it. What direction is it moving in? Isn't it going down? That means its weight is bigger than the tension. So, all right, so the angle is theta, tension and M1G. M1G is bigger. What about the force on M2? There's only one force in M2 because I'm assuming the plane is frictionless to make it easy. If that's the case, there's only one force, which is tension. Okay? And now, applying Newton's second law, the net force on M1 is M1G minus tension. Why am I taking it as M1G minus tension? Again, I told you, it's moving down, so M1G is greater. So we're not going with down is negative now, we're just going with logic. It's going down, this should be greater. So M1G minus T is M1A. Where did I get that from? The left-hand side is the net force, and the right side is Newton's law. Net force must be equal to mass times acceleration. Now for mass M2, there's only one force, which is T. So T must be equal to M2A. Notice that A is the same for both. And then my method of solving it is just to add these two equations. Like you can substitute, you get the same thing. But if you add, because you see a negative T here and a positive T here, when you add the left-hand sides, these two are going to cancel out, aren't they? Those two will cancel out, which leaves you M1G, and on the right side, you have to add these two quantities. So it'll be M1A plus M2A. I took A outside using the distributive law, or the reverse of that, and then divide both sides. So you get A is M1G by M1 plus M2. That's how you find the acceleration of the system. And let's just take some numbers. M1 is 3 kilogram. M2 is 2 kilograms. And then let's find the acceleration. Quite simple, isn't it? Once you think about it. So it's M1G. So it's 3 times 9.8 by 3 plus 2. So that'll be 29.4 by 5, which is 5.88 meter per second squared. Remember, in all these cases, you can never get more than 9.8. Because if it was freely falling, the maximum you get is 9.8. So you cannot get more than 9.8. That's always got to be less than that. So that's what I have for you today. Take a look at each of these questions. There's no use of memorizing these. But it's going to be very useful if you understand each and every step of this. So go over this video several times and try to understand. The key is to understand, not to memorize. So wish you all the best and hope you get much better grades on this exam. Thank you. Cut.